This is the second part of video 6. We're going to talk about sources of radioactive isotopes and half-life, the concept of the rate of decay of radioisotopes. Now, the type of decay matters, whether it's alpha, beta, or gamma when it comes to biological effects. Alpha does the most damage to the tissue, but has less penetrating power. So if the source is outside the body, you can normally protect yourself with protective clothing, but if the source is ingested or inhaled inside the body, it can be very bad because tissue damage will occur. Beta, it has intermediate penetrating power, but it can penetrate a few millimeters through skin, or a few millimeters, which could get it down into the skin. So if it's inside your body, it can do damage, and if it's outside your body as well. And gamma radiation has got the greatest penetrating power, so much so that it can go right through your skin and your bones, and it could pass straight through you, or if targeted to a certain part of your body, it can cause serious tissue damage to the point where it's used to actually kill cancer cells by destroying them. All right, so there's something about the penetrating power and whether or not the isotope that you're exposed to gives off alpha, beta, or gamma radiation. And the other factor that affects the biological effect is the rate of decay. How fast does the radioisotope undergo radioactive decay? Let me show you a little. This is a little animation showing what we mean by half-life or rate of radioactive decay. Here, the red dots show a large number of identical atomic nuclei that all obey the same decay law. And so let's just start this to show how this nuclei undergo radioactive decay. I've started it, and you can see as the red dots disappear, it's indicating that those particular atoms have undergone radioactive decay. And this graph here is showing the rate of decay. And as it turns out, all radioisotopes follow the same rate law or pattern. That means, and it's called first order rate kinetics, and it decays in this way. And because they all follow the same rate law, we can say that we can identify the half-life, the amount of time it takes for half of the radioisotopes to decay. So in this case, the half-life was 50 seconds. And so you could see if you go about halfway down to 50 seconds, maybe right here, let's see, whoops, we're having some problems with this. But anyway, it would be about right here. You can see 50 seconds would be half. And then in another 50 seconds, half of that sample would decay. And in another 50 seconds, half of that original sample. So if we increase the half-life to 100 seconds and restart the decay, you can see that the rate is slower. So the longer the half-life, that means it takes that much time for half of the original sample to disappear. So you can see that this is decaying the same rate law, but the time is longer for half of it to decay. So different radioisotopes have different what's called half-lives. They can be very, very short time spans or very, very long time spans, depending on the radioisotope. They all decay using the same rate law. It's just the time that the unit on the horizontal axis will be different. Okay, let's go back.